Welcome to another lecture of design of stair slab. In this lecture I will discuss how to design the slab of stair. So here the slab underneath the stair is designed as one-way slab for the expected live loading, dead load of RC slab, dead load of steps and dead load of floor finish. The thickness of the slab for stair is called its base dimension. Following points are to be considered. I will discuss briefly. Okay, first of all, here in the stair, the slab is inclined. So to take the load as an inclined, there is a formula. Okay, that is R square plus T square. R and T are the riser and tread dimensions. Riser square plus T square under root and divide by T, or you can just multiply approximately with 1.22. You will get the load of the inclined slab. Then you will calculate the load of steps. Okay, for the load of steps you will take the average riser divided by 2. Okay, then for the taking the minimum depth, here is a conservative approach. For the design of slab, you will take L by 35 for 280 and 300 grade and L by 28 for grade 420. Okay, and there are some guidelines against the detailing. Okay, that comes in the example. Okay, here in this stair, when you provide the bars that are in tension, there is chances that due to tension force here and here, this concrete covers fall out. Okay, the concrete cover can spall. Then there is a solution. The bars should be provided just like that. There should be embedment. The tension force that should be embedded upward, and the bar which is coming from the here in the downside go to the upward in the stair slab. So that's how we avoid in the detailing tension steel. Okay, so now I will start the example, and again the steps will also come in the example. I will discuss the example in detail. So let's start the statement with the statement of the design of stair. Design the first flight of the stair shown in figure 6.9. So let's go figure 6.9. Here is a figure 6.9 plan view of stair, for example 6.4. We will go upward. In this example, the design of one flight means from this to this end. Okay, not from this end to upward. Only one flight design is shown. Again comes to the statement. Design the first flight of the stairs shown in figure having a reinforced concrete footing at the bottom. Means when the flight start to the upward in the stair, the stair is supported at this point with the footing. Okay, that is a concrete footing, having a reinforced concrete footing at the bottom. You have to use concrete grade 18 megapascal and grade of steel 280 megapascal. Riser and tread dimensions of the stair, that dimensions definitely comes after the architectural design. Okay, that will decide what riser and tread dimension. So riser is 180 millimeter and tread is 260 millimeter. Select US customary reinforcement. Okay, first of all we will get the minimum depth or minimum thickness requirement for the slab. Okay, so let's first calculate the total span length. Okay, so there are 12 steps of 260 millimeter tread. So 12 into 260 millimeter means 0.26 meter. So length is 3.18 meter that of steps, and the landing is 1.2 meter. So the total length is 1.2 plus 3.12 meter. So here 1.2 plus 3.12. So total length of the stair slab, that is 4.32 meter. So H minimum considering both end continuous. Okay, here L by 35 for 280 grade. Okay, here in the slab the both end continuous how? Let's see, here is the detailing. Here is a concrete footing pad. So at this end the reinforcement is continuous in the from the footing to the slab. So this end is a fixed slab, and at this end this is a support type connection of landing, and then after this landing the slab will continuous upward. So it means the slab on one end that is fixed and on the other end that is continuous. So that's mentioned in the condition. Okay, H minimum considering both end fixed / continuous. So in our case one end fixed and continuous. So we will select L by 35. So that is 4320 millimeter divided by 35. So a minimum depth required for slab for design of stair, that is 124 millimeter. We will just round up it to 125 millimeter. So to get the effective depth, H minus 227 millimeter. What is in 27 millimeter? That is 20 millimeter is concrete cover and 7 millimeter is the half dia of number 13 millimeter bar. So our effective depth is 98 millimeter. So our next step is the calculation of load. So for the calculation of load, just like we do in the previous slabs, RC slab, the thickness divided by 1000 multiplied by 2400, we get the load. But in this case our slab is inclined, so we have to multiply with this factor, riser square plus tread square divided by 260, or you can multiply instead of this factor directly by 1.22, that is mentioned in the steps. Okay, you can multiply for the calculation of cell weight of stair slab, multiply with this, or you can multiply with this to calculate the horizontal plane load. Okay, our slab is inclined. To get the load in the horizontal direction, so you have to multiply with this factor, or either you can multiply with 1.22. So when you will multiply, you will get the answer 265 kg per meter square. That is the weight of slab. Okay, means this weighs slab. Now the load of these steps. Okay, how to calculate the load of step? We take the average of the step height, that is the riser divided by 2, that is average, then multiply with concrete density, then we will get the weight of steps. So riser divided by 2 multiplied by 2400 divided by 1000 to convert in a millimeter into meter. So our riser dimension is 260 millimeter, so that's why divided by 1000. So weight of steps, that is 216 kg per meter square. Now the last one is for the floor finish of this stair. Okay, floor finish of this stair, 15 millimeter floor finish, that is 15 divided by 1000 multiply with 2300 concrete density PCC. So our answer is 35 kg per meter square. Now calculate the total dead load, 35 plus 216 plus 365, you will get the answer 616 kg per meter square. That is just the detailing information that is I have explained earlier. Okay, now I will go for the live load. Okay, for the design of stair, in this example we have taken the load 300 kg per meter square. The live load depends upon the building to building. If it is a hospital building, is it a school building, office building, so you will select this live load from the table that is given in different codes. For example, you can select this live load from ASCE 7, that is a code, American Society of Civil Engineer, that there are 2 or 3 pages table from where you can select the live load. So in this example the live load is 300 kg per meter square. Now calculate the total factor load, 1.2 dead plus 1.6 live. Our dead is 616, so our live is 300. multiply with 9.81 divided by 1000, we get the total load, factor load, that is 11.96 kilonewton per meter square. So for per meter, divide with multiply with 1 meter, so we will get the per meter. As we have designed in the previous slabs or one-way slabs, we taken the unit strip for the design of slab, and then we, after designing one strip of the slab, and we distribute this strip to the whole slab. So that's why we have taken the unit strip, that is a 1 meter. So that's why multiply with 1 meter. Now to calculate the moment, our one end is continuous, so the moment is 1 by 10 omega L square. The Q is load omega. So our Q is 11.96. Okay, so when we put 1 by 10, 11.96 multiply by 4.32, that is our length. So our moment is 22.4 kilonewton per meter per unit strip. Okay, and the minimum for the tension control section for singly reinforced beam, that is also explained in the design of beams. So D minimum for singly reinforced section, moment divided by 0.205 FC prime B under root. So D minimum, that is 78 millimeter, and our D provided in this slab, that is 98 millimeter. So our D is greater, so that is a tension controlled slab of Stair. So now we have the moment. Now we will just apply the steel ratio formula. You can either use the hit and trial method, take the A value, then put in this formula, again calculate the A value, again put in this formula until the values are same, or you can directly put in this formula, exact formula to calculation of steel ratio. So steel ratio formula, that is rho omega, that is 0.85 FC prime over Fy. Okay, so that is the basic formula for calculation of steel ratio. 1 minus under root 1 minus 2.614, R is mu over BD square, mu over FC prime into BD square. So all the values are given. When you will put, you will get the rho value, steel ratio, and you will multiply with BD, and then you will get the area of steel. Either you can use this method or you can use the exact formula method. You will get the same answers. Okay, now the area is, we got the area of steel, that is 1000 millimeter square for 1 meter strip. So the here is the selected steel, number 13 at 120 millimeter center to center. Okay, area of number 13 bar, that is 129. Okay, so total steel required, that is 1000. 1 multiply with 1000. Okay, so our required spacing with number 13, 128 millimeter center to center, we have rounded down to nearest 10 millimeter digit, that is 120 millimeter. So the spacing is provided number 13 at 120 millimeter center to center. Then you will check the spacing requirement. The spacing requirement is same. Okay, here is a for spacing requirement 2H. Our maximum spacing requirement 2H, 300, 159, 6000 Fy minus 2.5 concrete cover, 126,000 divided by Fy, and we got the maximum spacing, that is 260 millimeter. Okay, so for when the slab is 130 millimeter, and in this example our slab is 125 millimeter. So when to multiply with 2H, you will get 250 millimeter. So our provided spacing is less than the maximum spacing, so it is okay. So that is the main steel. Okay, that is our main steel. Now we will get provide the temperature reinforcement. that is for 280 grade, that is 0.002 BH. So 1000 into H, that is 250 millimeter square. Again, you will select the criteria and the spacing and the temperature reinforcement, that is comes number 10 at 275 millimeter. Again, you will calculate the same way. This is the required area of steel. You will take the area of one bar, that is 71 millimeter square. Okay, 71 divided by 250 and then multiply with 1000. Okay, that require 284 millimeter spacing. So author has just rounded down to a little bit, 275 millimeter. Now our main steel and distribution steel is finalized in the stair slab. Now we will check for shear. Okay, our load is 11.96. that is simple. In the simple analysis of beams, we get the shear at the spot omega L by 2, but for designing we take at the location of effective depth. Okay, so that is Q into L by 2 minus D. Okay, so our answer is 24.66 kilonewton. Okay, why I have used D? You can see the previous lecture of design of beam in shear. You got the point why we calculated at D distance, and that is the applied shear. Then we will calculate the capacity by the approximate formula, that is 0.75 0.17 under root FC prime BWD. So our answer is 53 kilonewton. When we divide the capacity by 2, so we got the answer roughly 26 kilonewton. So our applied shear less than the half of the capacity, so means no shear steel is required in this slab. Now the curtailment distance is ln by 7, ln by 5, 0.22 ln, 0.3 ln. Okay, now first of all I will explain the detailing. Here is a slab, here is a footing pad. Okay, here is our main steel. Okay, you will see this is the main steel, that is longitudinal steel going upward and take a 180-degree turn. Similarly, that will go downward and go to the other side. Okay, so that is our main steel, that is number 13 at 120 millimeter center to center. Okay, so this author has provided the curtailment, some curtailments. Okay, so here you can see the curtailment of parts. So I will suggest do not curtail. The whatsoever the main steel comes, you will provide, as you can see, that bar will go straight upward and then take 180-degree turn, and the bottom steel in the landing area you will continue here up to ln by 0.3 ln. Okay, so you can continue in the inclined region 0.3 ln. Okay, on this side, and similarly on this side, here this bar I have discussed, and this bar you can provide at 0.3 ln and 0.2 ln. Similarly here, this bar you can provide at 0.3 ln or 0.2 ln. And now this is the waist of our slab, that is 125 millimeter, and you will also provide one number 10 bar under each step, like this, one bar along the width. Okay, and this under each step you will provide this bar is also of number 6 at 300 millimeter center to center. This will continue along the width of the slab. Okay, now the last one, that is the distribution steel. Here you will see this all steel is distribution steel. Okay, so that is provided at number 10 at 275 millimeter center to center. At the end there is you are saying 240 millimeter because at this point there is curtailment is provided, half steel is continue, half steel is provided. So I will recommend you, so do not cut, please provide throughout, so to avoid any inconvenience. So that's all for the stair slab design for stair. Okay, here that is again different condition. If your more rigidity or continuity is present at this end, the detail may be made as follows, but our case is this. Okay, and that is the final sketch of our stair slab design. So that's all for the design of stair. Have a nice day.